Welcome back to our lesson practice review. Today we're going through Chapter 3, Lesson 5, where we revisit something we've talked about in a previous lesson with even and odd functions. So what we focused on before with even and odd functions is really kind of looking at our graphs here and seeing that an even function reflects over the y-axis and the odd function reflects over the x and y-axes. We also talked about like having a table and representing these very basic, straightforward facts about even and odd functions. So the main ones we'll look at here are this property here and this one here, although this may come into play as well for the odd functions, but we're going to more focus on the equation part of it going forward. That's going to be kind of our level up here. And when we're given an equation, we may not know what the graph looks exactly like. And so we're going to use algebra to help us determine whether the function is even or odd. So let's get started. With problems 1 and 2, as a recap, we need to complete a sketch so that we can represent an odd function for number 1. Odd function has rotational symmetry, so it should look something like this, where if we were to rotate it 180 degrees around the origin, it would land on top of itself. Another way of looking at it is if we had this point here that was like 2, 4, then we should know that our point down here should be -2, -4. So we should have a graph that kind of goes through that opposite point here as well. For our even function, we're looking for something that reflects over the y-axis, meaning if we see something, again, the same point, 2, 4, then we're going to have a point over on this side, which is -2, 4, and we get this parabola looking shape here. For problems 3 and 4, complete the tables to match the descriptions. So the first one, we're given that it's an odd function, so that when we have a negative input, it gives us the negative output. And so when I look here to see what's in this spot, I just have to look for the negative input of that. So if we're starting with -2, we look at +2. We see that we get a -19. We want the opposite of that. So we're going to have +19. 0 could really be anything here because we don't want, I guess rotational symmetry has to be 0 here because this one's going to be the opposite, which is going to be +7, and this one here is going to be -35. So every, opposite input gives us the opposite output. For number 4, we got f of -x equals f of x. So every negative input gives us the same as our original output. So if I'm looking for the output for -2, it's going to give me the same output as +2, which would be 0. -1 will give me the same output as +1, which would just be 11. And +3 will give me the same output as -3, which would be -89. Number 5, determine if the function f of x is even, odd, or neither, and explain your reasoning. So when I do this, I'm going to kind of use those two equations. The first one, I'm always going to check even first because it's a little bit easier to see, hey, if I plug in -x, will it just spit out the exact same thing that I started with? And so I'm going to rewrite this equation here, but plugging in -x's. So in here, anywhere that I see an x, I'm going to use parentheses and put -x. And then once I have that input, I'm going to simplify that. And what I need to know in this situation is that -x times -x ends up giving me +x squared, because a negative times a negative is a positive. And so what this becomes when I simplify it is just 3 times +x squared plus 4. And we can see here that my f of -x is equal to my original function here, f of x. So I would say that this one here is even. For number 6, I'm going to do the same thing. I'm going to check for even first, and then I will move on. If it's not even, then I can check for odd. So first thing I'm going to do here is plug in -x for anywhere that I see an x. When I do -x times -x times -x, I end up getting -x cubed minus 3, because when I do this, I multiply 3 negatives, which still gives me a negative, and I notice here that this function is not equal to where I started. The next thing that we have to check for an odd function is we know that negative g of x should be equal to g of negative x. And so what we're going to do here is I'm going to take the original function here and multiply it by -1, basically. So I'm going to say negative x cubed minus 3. That would be negative g of x. And I'm going to distribute that negative to see if it looks exactly the same. So negative g of x is equal to negative x cubed plus 3. And again here, these are not equivalent because we see that this is negative x cubed minus 3. This is negative x cubed plus 3. And therefore, these two things are not the same, which means that it is neither. For number 7, determine if the function h of x is even, odd, or neither. We're doing the same thing. First, checking for if it's even. Negative 2 negative x to the power 5 plus 7 times negative x to the power of 3 minus negative x. And so when I do this, because I get an odd degree, there will be 5 negatives, which will end up making this negative. So I'm going to have negative 2 times negative x to the power 5 plus 7 times negative x cubed, because it's odd, right? Negative times a negative times a negative, and then minus negative x. And so the next step in simplifying this is going to be multiplying each of these terms together so that I get, if the values are going to be positive or negative. And so I end up getting positive 2x to the power 5 minus 7x cubed plus x. And so when I look at this here, and I look at my original h of x here, I would say that h of x is not equal to h of negative x. So the next thing I have to check is if I were to multiply it by -1, would I get the original function? So again, what I'm going to do here is I'm going to take this here and I'm going to multiply it by -1 because I want to see is h of x equal to negative h of negative x. So what I'm going to do here, negative h of negative x equals negative 2x to the power 5 minus 7x cubed plus x. I'm going to distribute this negative. Negative 2x to the power 5 plus 7x cubed minus x. And now I'm not doing super great on space here, but what we should see here is that negative h of negative x is equivalent to what we started with, our original h of x. And so therefore, this one here is going to be odd. Hopefully we go through another one in a little bit that will allow me to do this a little bit neater. But again, the first thing that I checked, just to kind of recap, is I said, hey, is h of x equal to h of negative x? Which I said it was not. And so then I said, hey, is negative h of negative x equal to my original function? And since this case it was, that tells me it's odd. All right, number 9, using each integer 0 to 9. Oh, I missed one. Number 8, the general equation for a linear function. If f of x is an even function, what can you conclude about m and b? So remember, a linear function just means that we have a straight line, right? So it could be a positive slope, it could be a negative slope, or it could be a slope of 0. The thing about it being even is it needs to reflect over the y-axis. And when we look at a positive or a negative slope, we see that this is never going to be the same on either side of the y-axis. The only time that it can reflect over the y-axis is when the slope is equal to 0. So I know that m has to equal 0 here. And b can really be anything, right? B tells me the y-intercept, so I could have a function that's up here, or I could have a function down here, and they would both be even because I could reflect them over the y-axis. And so m has to be equal to 0, and b can really be any number that you want. It doesn't really matter. Okay, now moving on to number 9. Using each integer 0 to 9 only once, create three functions so that f of x times g of x is even and g of x times h of x is odd. So in this one here, we need f of x times g of x to be even. So the way that we're going to do that is I'm going to pick some odd numbers here, 1, 3, 5, and 7. The reason that I do that is because if I were to multiply, x cubed, x to the power of 5, and x to the power of 7, if I were to multiply these two together, every time I multiply on the inside, all of my x to the power of 10, all of my terms would then be even. So in this case here, if I was doing f of x times g of x, that would equal x to the power of 10 plus 2x to the power of 8 plus x to the power of 6. And so in that one here, since all of these are even, when I plug in, a negative x, all those negatives end up going away. So I'm going to make sure that those are all odd. Again, if you used 1, 3, 5, and 7, great. If you use different numbers, also great. But as long as each of the exponents in f of x and g of x is odd, that will make f of x times g of x even. Next, we need to look at h of x. And so when I'm doing h of x, since I want them to be odd, I need to make sure that whatever I multiply g of x by, it would make all of those odd. And so I just need to pick two even numbers, right? So 2 and 4. Again, just to kind of show you what ends up happening here, we get x to the power of 5 and 7, x squared, x to the power of 4. Now when I multiply all of these out, I end up getting all odd exponents. So I get g of x times h of x, which is equal to x to the power 11 plus 2x to the power of 9 plus x to the power of 7. And so since all of those exponents are odd, that would give me an odd function. All right, next up, we got spiral review, problems 10 through 12. You use the function g of x equals 2x squared plus 3x minus 5. For number 10, we're going to rewrite the function in factored form. So I'm going to use my trusty box here. First term goes in the first box. Last term goes in the last box. I need to break 3x up into two numbers that multiply to negative 10x squared, which would be 5x and negative 2x. So 5x, negative 2x. I'm running out of room here. That's x, that's 5, and negative 1. So my factored form here for g of x is equal to x minus 1 times 2x plus 5. Determine the x-intercepts of g of x. Well, I've already got it in factored form, so now I just need to use my set it equal to 0, use the 0 product property, and set each of those pieces equal to 0 to get my first one, which is x equals 1, so 1 comma 0. And my second one, 2x plus 5 equals 0. I subtract 5 from both sides, divide both sides by 2, and I get negative 5 halves, 0. In number 12, it says sketch a graph of g of x. So I'm going to do a very basic graph here. I'm probably going to miss some points, but I'm just going to use the information that we are given and I'm not going to do too much extra because I'm just looking for kind of a general sketch. First of all, I know that it's positive, so I know that my parabola is going to be pointing up. I have my two x-intercepts that I found already, 1, 0, and negative 5 halves, which is right here. It says negative 2.5. And then I also, since I had it in standard form originally, I know my y-intercept when I plug in 0 for x is just going to be negative 5, because when I plug in 0, those other terms go away. And so I know I have this point right here. Now, also, I know that parabolas are symmetrical, and so I can see that the y-intercept here isn't going to be my vertex. So I'm going to kind of place it. I see it's a little bit more closer to the right. So I'm going to put, I don't know, something kind of like that. It's not the best sketch, but it uses the 3 points that we know for sure. And again, I know that my vertex is going to be halfway between my two x-intercepts. And so again, I kind of just estimated where it might be to give myself a sketch. So it's not perfect, but it gives us, the general shape of it. And it uses those 3 points that we know for sure are correct. So there's my kind of lazy sketch of a parabola. All right, that wraps up chapter 3, lesson 5. Next up will be lesson 6, where we start talking more about polynomials and their what we're going to call multiplicity. So hope to see you in the next video.